So let's talk about lead time variability. And let's look at some data here. And this is actually data from a sample of about 250 container movements on a common trade lane. So it's the same origin port and destination port move. And so we look at the distribution in time here for the movement from the origin into the origin port, the time from port to port over the water, and then the time from that destination port to final destination. And we can see what the distribution looks like. For the origin port, it goes anywhere from, that looks like, 2 days to almost 19 days. For the ocean, it goes from 9 to 13. And in the destination, it looks like it goes from 1 to almost 16. And you can see they're shaped very differently. So some things that pop right out, very consistent here on the port to port. Very inconsistent here on the origin port to port. And actually, this is demonstrating what's known as a bimodal distribution, where I have two humps. This happens a lot with ocean transportation. What's probably happening here is that a container comes in and it doesn't quite make it on that ship, so it waits a week until the next ship comes along on that trade lane. So you'll see this very often, this bimodal distribution, especially in international transportation. And in destination, I've got, it's unimodal, but it's still got some variability to it. So what we care about is not so much each of the segments, but the combined effect. And at the end of the day, I get a distribution like this, right? And so from this, I might know what the contracted transit time is, but I can also, let me change my color, look at what, I'll also have information about what the mean is, the average transportation time, as well as, right, the standard deviation of that transit. And so that's the data that I will have. And so the question is, how will I use that? So let's keep thinking about this, and let's go through a simple example. And this is something that we already know. So if I have a weekly demand that's uniformly distributed between 1 and 3, and my lead time is set, we've already figured this out from previous weeks. We can see what the expected demand will be. We know each day, or each week rather, the variability might be 1, 2, or 3 shipments, but we always know that there's only 3 weeks. Now, what we're doing now is not only is the demand variable, the time is variable. So I might have 6 weeks here. Time is on the horizontal axis, and every week I have this random number of packages or demand that happens. So it could be 6 weeks, could be 3 weeks, could be 4 weeks. So what I have here is what's known as random sums of random variables. My random variable here is weekly demand, right? And so over here, when I know it's always 3 weeks, I know I have this random variable of 3. It's either going to be 1, 2, or 3 each week, and I know there's always 3 weeks. Here, not only do I have my random number of shipments for demand each week, but there's a random number of weeks. That's why it's a random sum of random variables. So how do we handle this? Well, let's look at it mathematically. And so we're going to say that n is a random variable, assuming a positive integer values, 1, 2, or 3. Think of that, the number of weeks of transit time in our previous example. Xi is that demand, and it's an independent random variable, so the expected value for each period, each week's demand, is going to be the same for all of them. And what we want to find is all the parameters, the mean, the expected value, and the standard deviation of the sum of those demands from period I equals 1 to n. So what we're trying to figure out are two things. What's the expected or the average or the mean demand over that lead time, or the random variable over all of those random sums? And that's simply going to be the expected value of the number of periods times the expected demand or variable for each one of the periods. So En times Ex. And that's kind of intuitive. Everyone kind of gets that right. Where it's kind of tricky is to look at the variance. So the variance, we want the variance of this random sum of random variables, sum of xi from I equals 1 to n, where n itself is a random variable. And this is the equation. It's going to be equal to the expected n, that's the number of periods, times the variance of that x, that demand, plus the expected value of that demand squared, times the variance of the number of periods, n. Very convoluted formula, but let's look at it for a second. What are the units? remember the n is unitless. It's just the number of time periods, or the number of periods. So this doesn't have any units. This doesn't have any units. What are the units? Whatever x is. And for us, it's going to be demand. Items per day, items per week, pounds per month, whatever that is. And so it's going to be items per week or whatever squared. And this is the same thing. So it's each of the units here are going to be in units per time squared, because it's a variance. So let's do a really simple example. Let's say my n has a mean of 28. Let's call these days, right? So on average, it takes 28 days with a standard deviation of 7. My demand, my x, has a mean of 180 per each of these periods with a standard deviation of 68. So I want to figure out what's my mean, variance, and standard deviation of the sum of those x's over those n periods. So my expected sum, or mu sub s, is going to be 28 times 180, the mean times the mean. So that's telling me I should expect to have an expected value of s of 5,040. So again, that's pretty intuitive, and most people get that right away. But now we want to look and say, okay, what about the variance of this? And so if I look at the variance, I'm just going to use that same formula, and it's going to be equal to the expected value of n, the 28, times the variance of the x, which is just 68, the standard deviation squared, plus the mean of the x squared times the variance of the n, which is 7 squared. And that'll come out to 1.717 million. Take a standard deviation of that, or take the square root of that to get the standard deviation of 1310. So what have we done? For this simple example, I've told you that my expected value of s is going to be 5,040. That's the average, and the standard deviation of that demand over that lead time, or of that n, is going to be 1,310. So we're going to use this a lot, because this is a great way to incorporate variability into the total cost equation. Sometimes this is referred to as a Hadley-Witten equation, because as far as I could tell, that they were the first ones to apply it to inventory. But some of the assumptions, we assume that lead time and demand are independent random variables. And for definitions, we're going to use these terms. Mu d is the expected demand in items during one time period, whatever that time period is, days, weeks, months, whatever. Sigma d is the standard deviation of demand during one of those time periods. Then we're going to have the lead time. You have mu L is the expected number of time periods for that lead time, and the units of time periods need to be the same here, whether it's days or weeks or months. You have to be consistent. And sigma L is the standard deviation of time periods for that lead time. What we want to find is the expected demand of items over lead time, that's mu dl, and the sigma dl, the standard deviation of the demand of items over lead time. Now remember, when we talk about lead time, it's unitless. It has no dimension to it. It's just a multiplier based on the number of time periods, whatever that time period is, that your demand is determined over. So let's do a simple example. And here are the two equations I just did with our notation, that mu dl and the sigma dl. It's the same exact formula as on the previous slide. And let's do a transportation example. It'll look very similar to the example we just did. So suppose your lead time is 12 days on average and a standard deviation of 3 days. And your daily demand for an item is 100 units with a standard deviation of 22. I want to know my expected demand over lead time, as well as a standard deviation of demand over lead time. And this is going to be exactly what we just did. The expected demand over lead time is simply the average of the lead time, 12 days. That's my base unit. And the demand is going to be 100 units. This is daily demand here, 100 units. So 12 times 100 is 1,200. To find the standard deviation, I'm just going to take the square root of, it's going to be the expected lead time times the standard deviation, or the variance rather, of the daily demand. And here I'm just squaring it to get the variance. Add to that the expected demand squared multiplied by the variance of the lead time, which is just that standard deviation of 3 squared. I'm going to take square root of that and I get 309.5 or 310. So what have I done? I've determined that the demand over lead time is distributed with an average value, an expected value of 1200 and a standard deviation of 310. Now what I haven't done here is assumed a distribution. I haven't said whether this is normal, Poisson, or anything else. This is just averaging, taking expectations and variances. Now we will probably have to assume a distribution when I want to use this to figure out a performance level, because now that I have some parameters about the distribution of the demand over this random lead time, I can now set inventory performance metrics. And that's what we'll do next.